Hi, this is Tim Park. I'm with the Danfoss Drives Center of Excellence. I'm a senior application engineer, and we're here to talk about condition-based monitoring, specifically the commissioning of it.
Please take a moment now to pause the video to read the safety warnings shown here. Failure to follow these warnings could result in death or serious injury.
CBM is a software feature called condition-based monitoring. It's an outstanding use of drive technology to implement predictive failure monitoring in the VLT brand of products designated FC102, FC202, and FC302. This can allow you to minimize or eliminate downtime and manage the maintenance of your equipment in a cost-effective and timely manner. This can remove, if not eliminate, most causes of emergency downtime. The system focuses on the motor stator conditions and monitors change over time as the installation ages. Vibration monitoring is another key tenet in the system. We can quickly detect many changes such as loose mounting connections, bearing failures, and overall wear and tear. Load envelope monitoring provides us with a way to maximize efficiency and process optimization. We can schedule maintenance actions rather than respond to emergency failures. We're going to move forward with a video based on the use of the MCT10 configuration tool. The number of parameters that must be touched in this process, along with the number of parameters that will be gathered during the baseline data collection process, can be significant. To capture all the changes and support them effectively, the MCT10 tool will be a critical aid in getting the most from the CBM feature. Each of the three basic tenets of the system, motor stator, motor load envelope, and application vibration, which includes up to 2 channels, has an independent profile that has to be considered. If we go down to the MCT10 condition-based monitoring add-in, we'll find a group of buttons starting with baseline run and online baseline that constitutes our first decision point. And that decision is based on the application the drive is connected in. Let me just take a moment and discuss that in greater detail. The whole baselining process we have to appreciate is use together the normal operating conditions in the application. That is, as of today. It requires that we run the drive through the complete range of speeds that are required. We want to gain load and other performance data, and we recognize that we have to pull in speed information at the same time. In a pump or fan application, it's likely to expect that we can sweep the speed range in rather short order, maybe as little as a couple minutes, while in an application more related to an industrial process, we'll need to understand that process a little bit more specifically and recognize its general limits for speed and load. Knowing that, we may find that it takes a significantly longer period of time to record that data, maybe up to as much as 6 months. Getting back to our demonstration today, we're going to choose the quick baseline run and sweep the speed spectrum in a modest 1-minute interval. That's the quickest that we can collect the data throughout the speed range in question. Once we've made this selection, we'll press the next button. This will take us to the vibration setups. Up to 2 channels are available. we have input here a range for the baseline to take place. We're going to run from 100 RPM to 1800 RPM. We're going to select an evenly divided 20 points within that. So you get an idea here where we're talking about a real statistical sampling. So we press next, and the 1 minute selection is made here. We press next, and we're going to set up our first analog input associated with terminal 53 to be a vibration sensing point. And here we select, based on now the transducer data sheet, the range of vibration that it is capable of working within. And we're going to select G's here, or force of gravity. A53 minimum we're going to say is 0, and A53 maximum is 10 G's. Next. Now we're going to go ahead and create the baseline. We are waiting at this point for the drive to be started. I have the keypad available here, and we're going to press hand on, and you see the baseline start process underway, and the fact that we're logging the percentage of where we're at here in the bar graph as well. Were we to have had a second transducer, we could certainly apply that to the second analog input available at terminal 54, or if there were extra cards with analog input capability, they would show up as having choices available there as well. And the baseline process is complete. We have literally run the motor through the range of 0 to 1800 RPM and taken a significant quantity of data. The next thing we're going to move into is editing the thresholds. And they're all within this next button. And we'll start with the first one, which is stator. Now, as we go through here, a lot of this is already defaulted to where we're going to leave it. We're going to tweak a few of these parameters, but they have been proven in our field tests to be appropriate adjustments to make. There's personal philosophy at work here is don't tamper with success when you're talking about something like this. So we look at the choices we have to make here at the bottom. The first is interpolation type. The first button is for linear. The second one is a step response. These will not always be linear nor step response, but the one associated with stator monitoring, we do want to choose linear. We want to slip down to baseline characteristics, and we want to use mean. If you're not a statistician, that mean is also referencing average. Now, the next is related to an alarm. And my counsel to you is this. We are going into places that we've never been, and a reason for us being there is to try and provide the customer information that will allow him to better utilize his maintenance resources. If we introduce another device that will cause the process to be interrupted, that would defeat the purpose for now. Now, we may well find out in 6 months or 9 months that we need to come back and do something differently, but what I'm going to counsel you right now is we're going to make no changes, and we're not going to implement the alarm portion of this. We will slip on down to the warnings, and what we're going to choose here is just what we see in the default copy from baseline statistics, applying an offset. For warning 2, we're going to choose 4%. For warning 1, we're going to choose 2%. They are by default right where they're at. 2 others, stator resonance, we're going to keep that a copy from baseline statistics, and we're going to make that an offset of 0.05. And click the green checkbox to accept that change. And under stator resonance, we're going to choose 2%. Now, we could go ahead and press the generate button here. We're going to go ahead, though, and reset the rest of the statistical choices that we have to make, and then generate the thresholds after that. Finally, there's a time delay associated with each one of these warnings, and there's a separate entry for alarm time, but as we indicated earlier, we're not really going to engage those at this point in time. What we want to do is to select a time delay of 5 seconds on warning number 2. That constitutes a change from default, and we're going to leave the 10-second time associated with warning number 1 alone. Next, we'll move into the thresholds associated with the load monitoring. The interpolation time, again, will be linear, or interpolation type. We will move down to the baseline statistics, and the choice we'll make here is mean plus or minus 3 standard deviation. Again, a highly statistical oriented kind of an adjustment that we've proven to work in practice very effectively. We're going to ignore the alarm settings here again. We may cycle back and use these, but we don't feel it's in the best interest of your customer getting used to condition-based monitoring to have these active just yet. The potential for nuisance alarms is quite real if we don't get this right the first time. Under warnings, we're going to choose copy from baseline statistics applying factor, and we're going to make some choices here in terms of high and low warnings of 1.2 for warning high number 2 and 1.1 for warning high number 1. The low values will be set at 0.9 and 0.8 respectively. And we're going to make our time delay for warning number 2 again 5 seconds, just as we did during the stator setup. We can choose to generate here, and this button can be useful whenever we get after we're commissioned if we need to come back and make any adjustments. But we feel this is really a good starting point, and this is where we'll do the generation after we do the vibration setups. Finally, we're going to look at the vibration tab or tabs. For the sake of our demonstration, we've only configured one analog input to accept an input from a vibration sensor. If you recall, we set that up as a 0 to 10G transducer, meaning that vibration levels of 10G would be reflected as either the high end of what's coming in, or whether it's 4 to 20 milliamps or 0 to 10 volts. More than likely, it will be a 4 to 20 milliamp signal, but you can't say that definitively. You can go either way. So, we have the same issues that we had on the other transducers. We're going to look at interpolation type. Up to this point, everything we've said has been the linear interpolation variable. We're going to choose step with this one. The baseline statistics, instead of mean, is going to be min-max. As you might expect, we want to pick up on both extremes of vibration circumstances, whether they have become naturally high, or if the values just become excessive, or if they go to a minimum value. It may well mean also that you've lost a transducer or something to that effect. Again, the same warnings only versus alarms. We're going to ignore the alarm tab here. And we're going down here to copy from baseline statistics, applying the factor, and we're going to do warnings 2 at a factor of 1.5 and warning 1 at 1.3. And our time delays, we're going to make those both 5 seconds for warning 1 and warning 2. This will complete the threshold setups for our particular application. Recognize it again, there could be a second vibration sensor here, and the software is still evolving, so more useful things may be available in upcoming software releases. That being said, we're going to hit the generate button, and we will generate a whole series of new thresholds. And the process is complete. From this point, at the end of the vibration setup, or from any of our threshold configurations, we can always come over here and hit the home button. It will take us back to that opening screen under the condition-based monitoring tab, and we're going to select monitoring here. And the reason for this screen is to confirm this monitoring function. Until we make choices here, note the monitoring function is off. And under each one of these, we're going to go through and we're going to select warning as opposed to alarm and warning. This will again confine the use of CBM to providing warnings only, not adding any potential for alarm shutdowns as a result of this. Your user should understand that he needs to monitor the warning status of the drive either from the keypad or from field bus recognition of warning data being broadcast back to an operator's location. That being said, we're going to select warning here under stator fault, state of resonance active, state of resonance load. Under load, we're going to select warning for it as well, and for vibration 1. Vibration 2 we have not done any setups for, so we will just leave that in an off state. And we should be ready to go with that. And in closing here, we are going to provide you with an indication of what the monitoring screen can look like in real-time operation. We have simulated a vibration sensor on input number 1, or terminal 53, analog input number 1. Its value is represented here as X, and we have elevated it to the point where the LCP indication is the first vibration warning. and we can operate here without alarm and still transmit this warning to a control person and allow action to be taken on the problem. So note that the monitor screen also takes into account operational speed, and you see the current operating position incrementing across the display. So that's it for condition-based monitoring commissioning. Thank you for your time. Hope you find this useful, and have a great day.
Thank you for viewing. We hope this information has been helpful. Danfoss Drives can provide additional technical support, parts information, or repair services options by contacting us through one of the following methods. For immediate access to customer service or a technical support expert in North America, call 1-888-DANFOSS or 1-888-326-3677, or contact us through email. For technical support, the email address is drives.ts.na@danfoss.com. For customer service, the email address is drives.cs.na@danfoss.com. For after-sales service, the email address is drives.ts.service.na@danfoss.com. Additional information is also available on our website at www.danfossdrives.com. For contact information in areas outside of North America, please visit our global website at www.danfoss.com. Thanks again.